Ladies and gentlemen, welcome. Today my topic is the absence of the remote triggering in geothermal fields due to human activities. Geothermal field is an area of Earth with high heat flow, but here today we talk about is mainly about operational geothermal field with the installation of a geothermal system. The left figure I show you is about how a geothermal system works. The part of the high thermal water is that flash to a steam is separate and used to driving a thermal generator. We humans get power there, and the wastewater is injected back to the subsurface to keep the environment balanced. On the right figure, you can see some main geothermal fields in Southern California. Here is the Coso geothermal field, and this is the Salton Sea geothermal field, which we use as our study area. Operational geothermal fields typically have high seismicity rate, which could be caused by both tectonic and human activities. Due to this high background seismicity and possible interaction with fluid and seismic wave, the geothermal fields are recognized to be susceptible to the large remote earthquakes. As you can see in this figure, it shows the different sites triggered by the different larger earthquakes. The green one shows the Landers, blue shows the Hector Mine, and red shows Dinani. And take an example, the Coso geothermal fields is triggered by all three large remote earthquakes mentioned above, the Landers, Hector Mine, and the Dinani. But how the triggered earthquakes are distributed in the geothermal fields, how the human activities affects the remote earthquake triggering within changing the stress state. That's exactly what we want to know. Here we choose the Coso geothermal field as our study area, which is in the purple blanket in the left figure. On the right is our range of the operational Coso geothermal field. It is defined by the active injection and extraction wells, which are presented by the black triangles. Since 1987, the Coso geothermal field has been in operation and has a long-term geothermal fluid loss. And as you can see in this figure, the red one shows the extraction, and the blue one shows injection. The green one shows the net capacities of the geothermal production. We will focus on the remote triggering in Coso area following the 1992 magnitude 7.3 Landers earthquake. We obtained our original seismic data from the Southern California Earthquake Data Center and relocate this catalog by using 3D retracing, wavefront cross correlation, and the cluster analysis differential time method. We also calculate the magnitude of completeness to make sure the seismic data we study is complete. Declustering the catalog has also been done to remove the local aftershocks sequence. After we decluster the catalog, we do some statistic analysis, which including the calculation of the beta value of the seismic rate change and the Poissonian probability of the observed seismicity to analyze the spatiotemporal distribution of the remote triggering in Coso area follow the 1992 Landers earthquake. Here is what we got. By analyzing the regional catalog, we find that the operational geothermal field remain unaffected by the mainshocks, while the surrounding areas shows a vigorous triggering response. The left figure I show you is the beta value of the seismicity rate for the 30 days after the Landers earthquake relative to the background seismicity from the 1987 to 1993. The red refers to the high seismicity rate change, and the blue refers to low. From the statistical analysis, if the beta value is larger than 2, it would indicate a higher seismicity, significant higher seismicity relative to the background. In this caliber, we use the number 2 as a wide boundary between the red and blue. The same result could also be seen in the right figure, which you can see is made of the 7 figures. The red dots are it shows the daily seismic rate in 7 sub-areas, which could be matched in the 7 regions in the left figures one by one. The red dots are the earthquakes which the magnitude are less than 4, and the green dots are the earthquakes which magnitude are larger than 4. The blue line marks onset of the Lander earthquakes. As we can see, the 6 below figures shows a significant increase after the Landers earthquake, while the first figure, which refers to the operational geothermal field, do not. As we all know, that earthquake triggered by a seismic wave of the remote large earthquake could be used to detect the critical loaded faults. The phenomenon we observed could be only interpreted into a less critical stress state in the operational geothermal field compared to the surrounding areas. Here our question comes: why? We assumed the tectonic strength affects all areas in coastal area equally, and the difference in stress states could only attribute to the human activities, which is geothermal production here. We defined our critical fault strength as the formula here and give our interpretation. The tau 0 is the fault strength, F is the friction coefficient, sigma is the normal stress, and P is the pore pressure. As we have seen above, since the 1987, the coastal geothermal field has in operation and has a long-term geothermal fluid loss. And this geothermal fluid loss could result in a decrease in pore pressure and increase our fault strength. With a higher critical fault strength and the same stress change, a new, less critical stress state forms. But a less critical stress state seems contradicts to the high seismicity rate. Could these two situations coexist? The answer is yes. Let me explain. We have investigated the spatiotemporal of the seismicity from the 1981 to the 2011. We divided the seismicity into a shallow layer, which is less than the 3 kilometers, associated the human production process, and a deep layer, which is confined with the between 3 kilometers and 10 kilometers. Our result has shown that both the seismic rates had decreased immediately following the onset of the geothermal production in 1987. And the drop of this seismic rate is consistent with our explanation that the reduced pore pressure after production increased the fault strength in operational coastal geothermal field. With the geothermal production grow, the seismicity rates in the deep layer has remained low, and the seismicity rates in the shallow layer recovered and increased to a high level. The shallow geothermal increase in seismicity has been proposed to result from the contraction of the reservoir and the local effects such as the diffusion of the pore pressure from the injection well and the temperature change. And considering the reservoir sitting in a less critical stress state, we propose that this increase in shallow part is more dominated by the highly heterogeneous perturbations. We also do some analysis on another study area, which is the Salton Sea geothermal field. This is, we studied this remote triggering following the 1999 magnitude 7.1 Hector Mine earthquake. It has a similar geothermal production history with the Coso geothermal field and the similar tectonic settings. We can also see the surface subsidence observed by the INSAR is quite matched to the range of our range of the operational Southern Sea geothermal field defined by the active injection wells. The result is the same. There exists absence of the remote triggering in this geothermal field, and the surrounding areas shows the vigorous triggering response. This is my summary, and this is my future work. I will stop here and take questions.